So you can see it there. So it is saying 10 milliliter of 0.12 molar solution of sulfuric acid was taken in class and added few drops of indicator. So it's saying 10 milliliter of 0.12 molar solution of sulfuric acid was taken. So this is standard solution. Yeah. So we know the volume, we know the molarity. So it is called standard solution. Have you got that? Because we know everything about this solution. Yeah. So this is the guy where we know everything about this solution, and we take 10 milliliter here, 10 milliliter of sulfuric acid here, and then we know this is the volume, right? So the V1 is this one, and the molarity of this solution is M1 is 0.12 molar, right? And then and added few drops of indicator. So if you put a little bit of indicator here, that becomes a red in color. This is a red, or that becomes pale in color. So it put a couple of drops of indicator. So indicator is it gives one color in acidic environment, and it gives another color when the acid is gone. Makes sense? So that's called the indicator. Have you got that? So that's a indicator. Put 2 drops. So this is not the reactants. This just shows the whether this solution is acid or base. So if it is red here, this is acid. So if the red color is gone, that becomes the base. So it becomes so there are some indicator that becomes yellow in acidic, yellow in acid, and the yellow color is gone. It becomes the colorless in base like that. Yeah, and some becomes pink in base, and color is gone in acid, something like this. You see that? So it gives one color in acid and another color in base. So that's the indicator. So like that, and then you put so burette. So in this burette, so this is called burette. All right. So this is called burette. In this burette, we put so this is the acid down here. So this is the acid. We put base here. So this solution is the base solution, and that base solution is a sodium hydroxide solution. So we put base solution here. So we put base solution here, and so 0 is here. So 0 milliliter is here, and maybe 10 milliliter here, 20 milliliter here, 30 here, 40 milliliter here, 50 milliliter here. So it is written like this in the burette. Everybody got that? So you will see in lab number 7 this exact experiment. Yeah. So this is sodium hydroxide. We put sodium hydroxide here, sodium hydroxide here. So we don't know the molarity of this solution. We have a lot of sodium hydroxide solution here, sodium hydroxide solution here. I can measure whatever volume I want, but I don't know what is the molarity of this solution, right? So we need to standardize this solution. Everybody got that? So because I know the volume is what? I know it, but molarity, how much sodium hydroxide is in 1 liter of solution? I don't know. Make sense? So I need to standardize. So I put the sodium hydroxide here all the way up to 0 here, and it is closed here. Make sense? So it is closed here. I put all the way up to 0, meaning that from here to here there is 50 milliliter of solution. I put the indicator here, and it's if it says the color, oh, okay, it's a colorless. So in the indicator, it is a colorless now. So no color here, colorless. So no color, just like the water color here. Make sense? Now I start to open this. This is called stopcock here. I open a little bit, and few drops of base drops here, and it turns tiny pink, and the pink color just disappear. And I again open this one and let a little bit go down here, and it becomes pink, and pink color disappears. So I just keep doing, and when I put all the way up to this 30 milliliter mark, when I reach up to 30 milliliter mark, just the pink color appear here. So it's become now pink, or you can write the red. Everybody got that? This is the whole idea. Yeah, all the titration is done this way. So when 30 milliliter of this is from 0 to 30 milliliter is gone down here, the solution just become pink, and the pink color now does not disappear. Make sense? So now this solution just become basic. So we didn't put a lot of base, it just turned to be the basic. So that is called the end point. Make sense? In all acid is eaten by the base and it just become the basic. Everybody got that? So that's called the end point. When the acid and base just react to neutralize, that is called the end point. So it is the end. All right. So how much volume I put from here to here? That is a V2. So V2 is 30 milliliter. So that base is 30 milliliter. And then what is the molarity of NaOH? This guy, I don't know. That's M2. Because I put this guy here, right? So mainly I don't know the molarity of that guy. Make sense? But I know V1 and M1. Now my reaction is, now you need to look the reaction. The reaction, our reaction here is this reaction. Look here. So this is H2SO4 plus NaOH giving Na2SO4 plus plus the 2H2O. Now look the balance here. When they balance, the reaction is 1 and 2. 1 is here, 2 is here, and like this. This is a balance. Now again, we I already told you our moles, the molarity M is equals to number of moles divided by liter, right? So this is our formula. Make sense? Molarity is equals to moles by liter, right? So if you take this volume, so liter is basically volume. You can write the milliliter or liter here. It doesn't matter because we are using milliliter here, molarity here, milliliter here, molarity here. So it doesn't matter. You don't have to convert milliliter to liter in this case. Make sense? You just write the volume. So volume. So volume multiplied by molarity gives the number of moles. Everyone got that? Volume multiplied by the molarity gives the number of moles, right? Look here. So how many moles I have? Actually, it's a millimole. So this is V2M2. So basically, this is a mole here. So this is V2M2 is what? The base, right? NaOH. This is for NaOH. And V1M1 is acid. So this is acid. So V1M1, right? Number of moles. If you remember, if you go back to all the reaction we did, all the time we were writing the moles here, right? Moles, and this is moles. The moles and moles, right? So here V1M1 is the moles. Everyone got that? So previously I was taking gram and converting that 1 mole is equals to how many gram, and then that mole I was putting up here, right? But here V1M1 is a mole. And then V2M2 is the mole of this one. V2M2 is this mole. V2M2 is the mole of NaOH. Everyone got that? Now take the ratio here. You see that? The ratio? What is the ratio here? The formula now becomes V1M1 by 1 is equals to V2M2 by 2. Did you get this point? All the time that upper number divided by the lower number, upper number divided by the lower number we have been doing, right? It's the same thing. Everyone got that? So what is the V1 here? V1 is 10, M1 is 0.12. So this is 10 multiplied by M1 is 0.12 divided by 1 is equals to V2 is 30, and M2 is M2, and then I have 2 here. So 2 here. So 2 there. You see that? Now 2 goes this way, and then 30 goes this way, right? So that becomes 10 multiplied by 0.12 multiplied by 10 multiplied by 0.12. This goes there, multiplied by 2 divided by 30 is equals to M2. So this is the molarity of this NaOH solution. Everybody got that? So V1M1 is nothing. It's just the number of moles, right? V2 number of moles of H2SO4. V2M2 is number of moles of NaOH. Yeah, good. So if this, so what is this one? So this is 0.08. 2 multiplied by 0.12 multiplied by 2 divided by 30 gives you 0.08 here. So that is 0.08 molar is the NaOH solution. You got it? So now let's do this reaction for another one. So exactly same thing. I'm going to do another reaction here. So instead of sulfuric acid, and now I'm going to use HCl here. So HCl, yeah, like that. So exactly same thing, but I'm not using sulfuric acid now. I'm using the hydrochloric acid as my standard solution. Everyone got that? So what happens in this case? Now let's write that reaction here. So all everything is same. So I'm going to write that reaction. So I have in that HCl, and then I have NaOH, and then I'm reacting these two together, NaCl plus H2O. Now look here, is it balanced? One Na, one NaOH, OH, H2, two H2, and one O, one Cl, one Cl. It's already balanced, right? There is no two factor there. Make sense? Have you got that? Now here is one, here is one, here is one, here is one. Now the HCl is the number of moles of HCl is M1 V1, right? M1 V1. Make sense? Mass multiply, molarity multiplied by the volume gives the number of moles. Here actually number of millimoles. Why millimoles? Because I'm using the milliliter, multiplying the molarity gives the millimoles. And if you divide the millimoles by 1000, it becomes the mole. It's the same thing. Yeah. So look here. So M1 V1 and NaOH, I'm using M2 V2. So this is exactly same thing. Now look here. What happens to our equation now? M1 V1 by 1 is equals to M2 V2 by 1. Previously there was a 2, right? You got it? When there was a 2 S2 S4, there was a 2, right? Now I have both sides 1 1. Yeah. So there are a lot of problem in homework. You will get idea what happens there. Yeah. So I put those like that way. Now look here. What is M1? M1 is 0.12. V1 is 10 divided by 1. M2 is, I don't know what is the molarity of NaOH, but I know the volume. Volume is 30 ml. 30 ml. And then divide by 1. So 1 goes this way, or 1 cancel. It doesn't matter. That one 0.12 multiplied by 10 divide by this 30 goes here. That is equals to M2. Look here. So previously 0.12 multiplied by 10 multiplied by 2 divided by 30, right? When I was using the S2S for exactly same problem. Now I'm with HCl, I'm doing 0.12 multiplied by 10 by divided by 30. There is no factor. Make sense? So that's the difference. Everyone got that? So we need to look this reaction and put those ratios. Got it? Can you do it? Very important, yeah? So like that. So now let's do another one. Same thing. So I think in the previous slide, before this slide, I put this problem M1 V1 equals to just M2 V2 without 2 there. So let's go to another one here. So I don't do this one. So let's do this one here. 15 ml of 0.1 m sodium carbonate. Look here, volume is given 15 milliliter, and molarity is given 0.1 molar. So it is standard solution. Make sense? Both number are given, meaning that this is standard solution. You got it? So both number are given here. So the standard solution, I put it here, and that is V1 is how much is V1? 15 milliliter. So I have 15 milliliter here, and then so this is sodium carbonate, and then 0.1 molarity. Molarity is 0.1 molar solution here. I put it of sodium carbonate, Na2CO3 solution here. Everyone got that? Same thing. So because I know both of these ones, so I put it here. Yeah, I know volume and I know molarity. Now a drop of phenolphthalein indicator was added to it, and pink color appears, so it becomes pink. So now initially it is pink. So when I put acid, so this is pink now. So what do I feel it here? Here they are saying HCl was added to it from the burette, and 25.6 ml of acid react to the end point. So 25.6. So here, somewhere here, 25.6 ml acid. So this is HCl. This is HCl. And when I drop this one, and when it is from here, it is 25.6 ml here, the pink color just disappear. You see that? Previously, it was with color. Now, when I put the acid to this base, the pink color just disappeared, meaning that I reached the end point. All sodium carbonate is eaten by that acid. Everybody got that? So that's the indicator. So that's how we do. When you do the experiment in 7th, I think lab 7th, you will see. Yeah. So we will do this one now. So how much acid we put from there? From there, the acid we put here is 25.6 ml. 25.6 ml we put it here. And what is the molarity of HCl? I don't know, right? Everyone got that? So now let's write the reaction. So the reaction will be like this. So Na2CO3 plus HCl and it gives NaCl, water and carbon dioxide. NaCl, water and carbon dioxide. You don't have to understand this reaction. It's not your business. I will give that reaction there. You just need to know how to calculate. Yeah. So it's a balanced reaction will be there. Now is it balanced or not balanced? Let's look here there. 1, 2, 2. So here is 1, here is 2, and then here is 2, like this. Now it is balanced. Now look here, sodium carbonate is here. That's M1V1. So I'm going to write M1V1 here, right? Sodium carbonate here is M1V1 here. So this is nothing. This is just the number of moles. M1 multiplied by V1 gives you number of moles. If you use the liter, M1 multiplied by that liter gives number of moles. If you give the milliliter, that's the number of millimoles. Is the same thing, yeah? The millimoles. Now this is M2V2, M2V2. Now, now let's take the ratio. M1V1 by 1 is equals to M2V2 by 2. Now you can easily put the values there and you can calculate what is unknown. Everybody got that? Easy, right? Good. So what is M1V1? M1V1 is right there. So M1 is 15, V1 is 0. M1 is, so this is M1, this is V1, then is equals to M2. What is M2? I don't know. What is V2? I know, 25.6. And then there is a factor 2 down here. So this 2 goes this way, 15 multiplied by 0.1 multiplied by 2 divided by this 25.6 comes down here is equals to M2. So you just put this number in calculator and you get the molarity of HCl. You got it? So most important is this formula. So where should I put 2? So if you write this way, you easily know where to write 2 and where to write 1. You got it? Very simple. Yeah. It's a lifetime learning. Once you learn here, you all the time you do the same way. Yeah. But if you start to look the different book has different approach and they just keep doing calculation, explaining things, number of moles, whatever. It's very, they confuse you in the book. Yeah. So this way is the most easiest way. You got it? So, like that. So, all right. So you come 0.117 there. So there is another way also. So I think you can do all like this way. Yeah. So there is I think another problem. So let me see if I have another problem here. So I am doing 2 ways here, but I'm not solving 2 ways. Only 1 way I saw. Yeah. I show you. Yeah. M1V1 by M2V2. So you can do that way. So let me see if there is one problem here somewhere. Chapter 4. I don't know if I have it. Definitely there is a one problem in homework. So it's not it's a gram. So this one. So here I have one problem here. So I'm going. So this problem is in homework. So let me show you how I did here. So let's do this one. So this one is how many milliliter of 0.247 molar potassium permanganate solution would be required to fully react with 50 milliliter of 255 millimolar solution, right? So look here. So this is known. This 50 milliliter is given and 255 millimolar is given, right? See that both number are given. So this is a standard solution, right? So I put this in a flask here. So I don't solve here how I am showing here in the in this slide. Yeah, I do different way, a little bit different way. You will see. So let's do this one. So there is a homework problem. When you do it, you will understand what I am talking about. So look here. So how many milliliter of 0.247 m potassium permanganate solution would be required to fully react with 50 milliliter of 250? So here we put 50 milliliter of potassium permanganate. because this is known, both number are known here. You see, this is V1 and another number is also known, 255 millimolar. So M1 is 255 millimolar. So sometimes they give the molarity, sometimes they give the millimolar. It's the same thing, yeah. Millimolar is a dilute, more dilute. Molarity is more concentrated, right? So so how many milliliter of 0.247? So this here they put this solution is 0. So let's say M1 is 0.247 millimolar or this is a molarity. So this is molarity, and then if so M1 is given here, but when I put it here, what is the required volume? How many milliliter I should put from here to here so that the color just disappear or just appears? If there is already some color, that color should disappear when I put from here to here, right? Or if there is no color, I keep putting here and this color just disappear. Make sense? So how many milliliter I should put from here to here? So V1, I don't know how many milliliter I should put from here to here. So maybe 20 milliliter, 30 milliliter, 40 milliliter. How many milliliter I would put from here to here so that if there is a color, color disappear. If there is no color, color reappears. Color appears. Make sense? So that's the indicator. Everyone got that? So like that. So one thing you need to know is that here is a millimolar. Here is a molar. You see that? This is a molar. This is a millimolar. So millimolar should be converted to molar because we need to have the same unit here. Molar, millimolar, right? So 1000 millimolar is equals to 1 molar. It's the same as 1000 milliliter is equals to 1 liter. Make sense? So let's convert that one, 0.255. So that is 255. Is that 255? Yes, 255 millimolar. So I don't need millimolar. So I put this factor 1 molar up, 1000 millimolar down. You already know this kind of calculation. So millimolar cancel. So 255 by 1000 give you 0.255 molar. So this is 0.255 molar now. Now they become same unit. Everybody got that? So there was a molar. So I make this as a molar so that I can use the formula easily, right? We need to have the same unit. Everybody got that? Good. Alrighty. Now, what is the formula to M1 V1 is equals to M2 V2? What kind of formula is there? So I'm not going to do it here like that way. So let's write the reaction here. So our reaction here is this is a potassium permanganate, MnO4 minus. This is potassium permanganate, and then this is iron. This is 5Fe, 5Fe2. So when you do the reaction, it looks like this way. I'm not even writing these things here. Yeah, there are a lot of things here. You can look in the board. So you really don't need these things. Make sense? So so this is the when you balance the reaction, there is 5, there is 1. Look at the slide over there. Now 1 here, 5 here. Again, the same thing. So look here. So M1 V1 is this one here is potassium permanganate, MnO4, and then this one here is the iron sulfate, Fe. Oh no, that's a iron sulfate. This is iron sulfate. This one is iron sulfate. Sorry for that. Fe2SO4. So this is iron sulfate. So both things are known for iron sulfate, right? FeSO4 or Fe2SO4? FeSO4. So this is FeSO4. This is potassium permanganate. See that for FeSO4, both things are known here. 50 milliliter, 0.255 millimolar. So these both things are known here in this flask here. So only one thing is known here, that is M1 is known, V1 is known, not known. How much volume I should put from here to here so that color appear, or if there is color, color disappear. Make sense? So this is MnO4. So this is KMnO4 here. So I'm going to write M1 V1 here. So M1 V1, and then so I'm going to write, if this is M1 V1, this should be M2 V2, right? This is M2 V2. So M2 V2. Now my equation becomes M1 V1 by 1 is equals to M2 V2 by 5. Everyone got that? It's very easy. You got it? So if you write M1 V1 M2 V2 here, you write M1 V1 here. If you write M2 V2 here, you write M1 V1 here. Same thing. It doesn't matter. Yeah. So M1 V1 is just to come to formula. Yeah. And then if you see that, so this guy is a potassium permanganate. So I know M1. I don't know volume. So M1 V1 gives the number of moles here of this guy, and M2 V2 gives the number of moles of this guy. So number of moles, number of moles. So 1 mole is equals to 5. This many mole is equals to this many moles. So I take the ratio M1 V1 by 1 is equals to M2 V2 by 5. Now you solve the problem. So M1 is 0.247 and you don't know V1. So 1 is here, 1 goes this way. So you don't need to multiply by 1 there. So M2 is what? M2 is 0.255 and V2 is what? 50 and divide by 5. So 247 comes down here. So V1 is equals to 0.255 multiply by 50 divide by 5 and then multiply by 0.247. So this is the amount of the this solution that you need to put down here, so that if there is a color just disappear. If there is no color just appears. Make sense? Everybody got that? How I come with this formula here? M1 V1 by M2 V2 by 5. Yeah. So like that way. Yeah. So this is the most easiest way of doing things. So let's look here. How much I'm getting 10.3 here. So do I get the 10.3? So it looks like I get. So 0.24 and 0.25. This cancel. 5 10s are 50. So 10 milliliter, right? Make sense? Look here. 0.247 and 0.255. They are almost equal. So this and this cancel. And 50 by 5 gives about 10, right? Got it? So this is the most easy way. And this kind of problem I have put in the homework number 4. So you just do this one and then you get the answer. Everybody got that? Good. So this is very important. So so I was teaching this way in the first semester. I come here, so everybody got very confused here. So this way is a more easier way. M1 V1 is the number of moles. So take the ratio and then solve for what you don't know. Got it? Good. All right. So I'm going to do a couple of formula here. So just because this titration, this is called titration. Yeah. So the process what I showed you now is called titration in chemistry. Yeah. Titration. I don't know where does that word come from, titration. So we know molarity and volume of one thing, and we know the volume of another thing, but we don't know the molarity, and we find the molarity by doing this kind of the operation, and this process is called a titration. Yeah, T-I-T-R-A-T-I-O-N, titration. So let's look a couple of reaction and come with some formula here. So NaOH. If you are doing NaOH and HCl, titration NaCl and H2O. Look here, this is balanced, right? Already balanced. Na1, Na, O is O, O is O, H, there are 2S, 2H, 1 Cl, 1 Cl. In this case, there is one. So if this is M1 V1, this is M2 V2. So if you are doing the 1-to-1 reaction, the reaction would be M1 V1 by 1 is equals to M2 V2 by 1. 1. So 1 you really don't have to write because 1 does not do anything. Everybody got that? So if the reaction is 1-1, equation becomes very simple. M1 V1 equals to M2 V2. You got it? So let's say we do another one here. NaOH is reacting with let's say something S2SO4, S2SO4 like this. So now here you just balance this reaction, Na2SO4 plus Na2SO4 plus H2O. Now balance the reaction, Na2 here. So you need to put 2 here so that the reaction gets balanced. S2SO4. So SO4 here, S2 here. So this is 1. Now look here. So if this is NaOH, if you give the NaOH as M1 V1, S2SO4 is M2 V2. Now your equation becomes M1 V1 by 2 is equals to M2 V2 by 1. Make sense? You just look the number balance and put those number down there. You got it? Like that. So if you see something like this, let's say calcium carbonate. Let's say you are doing some reaction between calcium carbonate and hydrochloric acid. Let's say this is CaCl2 plus H2O plus CO2. Let's say these are the both are the, this is also solution, this is also solution. Now let's balance this one. 2 here, 2H2Cl, 2H2CO2, CO2 and 1. Look, now it's balanced, right? Now this is also solution. Let's say this is also solution. It's not solid now, right? I put this in water and I have the molarity value of calcium carbonate. Make sense? So now this is one. So what would be the formula for this kind of the reaction? So you put, if you put M1V1 here, M2V2 here, this is for hydrochloric acid, this is for calcium carbonate. Take the reaction, take the ratio, M1V1 is equals to M2V2 by 2. You got it? So that's how we come with this formula. Make sense? You got that? So you need to look the reaction and just put the multiply the hydrochloric acid volume and the molarity of whatever the volume and the molarity, put that there, and then multiply the molarity of this guy and the volume of this guy and put it there, and just take this ratio, and whatever you don't do, just calculate that one. Yeah, so this is the most easiest method of doing things. Yeah, and if there is a millimolar one side, molarity on the other side, you need to convert to the molarity for both, or millimolar of both. Yeah, got it? So like that. And I just showed you. So I was showing you 5. So when we were doing the this thing, you see that 1 MnO4 was reacting with 1 MnO4 was reacting with 5 FeSO4. So volume and molarity of FeSO4 was, let's say you put M1V1 here, volume and molarity of MnO4 is, let's say M2V2 you put there. So M2V2 by 1 is equals to M1V1 by 5. So this way, yeah. So whatever the things are reacting, whatever the coefficient is, just take the ratio. Everybody got that? That's how we get the answer. So when you do the homework, you will definitely know this. But in dilution, when you are diluting one solution, this formula is always M1V1 is equals to M2V2. One dilution problem. So dilution means, I told you, so let's say this is a bottle here. You have a, let's say 12 molar HCl here. Now you want to make, let's say 1 molar of 500 milliliter here, 500 milliliter, 1 molar solution of that one. So this formula is always M1V1. It's not a reaction. Yeah, we are just diluting. So I take some from here and put it there. So let's say I put V1 amount from here and put it there to make 500 of it. So I know the molarity of this one, and then V2, I know the 500 ml, that's 0.5 liter. Or if you want to put the milliliter in the same unit, same thing, 500. So if you take the milliliter there, and then M2, you are making 1 molar there. You see, now what is the molarity of this guy? You can easily know. V1 or molarity, you already know, 12 molar, and V1, how much you should put from here to here. You see that? So if you are doing just the dilution, use V1 is equals to V1 M1 is equals to V2 M2. If you're doing the reaction 1-to-1, like 1 NaCl plus 1 HCl, when you do the balancing 1 in 1, V1, this equation is V1 M1 equals to V2 M2. But when the coefficient is 1-to-2, 5-to-1, you need to do the formula that way. Yeah, got it? Like that. So we are done with the chapter 4. Now I start the chapter 5. So let's do chapter 5. Chapter 5 is about thermodynamics. Yeah. So chapter 5 is about thermodynamics. So thermo means heat, dynamics means flow. Heat flow is called thermodynamics. Make sense? So heat flow is called thermodynamics. So let's say I have an oven here. So oven in a house, we have an oven in kitchen, right? I have an oven here and I have a water here. So let's say water. So if I put this top here in the oven, so the heat will flow from heater to water. So this is called thermodynamics. Make sense? So from where to where the heat flows. So heater is much hotter, very hot, and water is cold. So heat always flow from hot object to cold object. Make sense? Heat always flows from hot heater to cold water, right? Make sense? Good. So let's say I have a water here, hot water. So I have hot water here, and I put it in ice. So this is ice, cold ice, right? So where does the heat go? Heat goes from here to here or here to here. So heat goes from hot to cold. Everyone got that? So that's our everyday experience, right? Heat always go from hot object to cold object, right? So heat goes from outside. Now outside is cold, right? Inside we have hot, right? So heat always goes from inside to outside. Therefore, we need to have multiple doors in the house. Yeah, so that the heat cannot go from inside to outside, or we need to close the door. So that is called thermodynamics. So heat flows from hot object toward cold object, and the study of this flow of heat is called thermodynamics. Make sense? Thermo means heat, dynamics means flow. In thermodynamics, we study about heat flow from one object to another object, and heat always flows from hot to cold, not cold to. Yeah. So what is energy? So energy is basically capacity to do work. Yeah. So if I drink a lot of protein and come here to do work, and I can really work a very smart way, right? Strength. So the capacity of doing work is called the energy. Make sense? But if I don't eat food, so I am so tired and I don't have enough energy to do work, so I don't have much energy. Yeah. So capacity of do work is called energy. Make sense? That now. What is thermal energy? Thermal energy is basically the heat transfer. The heat is transferred from one object to another object, and it does the work. So transfer of heat is called heat energy. So let's look here. So what is kinetic energy? So anything is moving and it has some energy. That energy is called kinetic energy. Yeah, a car is moving. So the energy in the car is called kinetic energy. Make sense? So I'm also moving. So the energy I have is a kinetic energy. But you all are sitting, the energy you have now is a potential energy. Make sense? So if anything is moving, the energy contained by it is called kinetic energy. Look here. So this guy now is sitting in my hand. So this has the potential energy, right? So now I just throw it down and it would move down. And when it was moving, it's a kinetic energy. Make sense? So if something is moving like that, so kinetic energy. If it's just sitting like they're doing nothing, that's called the potential energy. Make sense? So energy in sitting object. So an object is not moving. There is an object, and object is not moving. Object is not moving. Moving, that means it is at rest. So if it is a rest, the energy it has is kinetic energy. The energy with this guy is potential energy. Potential energy. Make sense? Potential means position, not moving. Yeah. So if something is just doing nothing, not moving, just sitting there at rest, and all the energy it has is called potential energy. Good. So, but if object is moving, this is called kinetic energy. So an object is moving now, is not in this, right? If an object is moving, the energy it has is called kinetic energy. Make sense? I'm just changing the word. Yeah. If the body is moving, it has kinetic energy. If the body is at rest, it has potential. That's it. Yeah. Now, how to calculate the kinetic energy? So let's calculate the kinetic energy. This is a football, and you kick this football from here with some force, and this guy has, let's say, 1 kilogram mass. So mass is 1 kilogram, and then it starts to move with, let's say, 3 meter per second velocity. So velocity, see that? So you can measure the velocity of this guy and the mass of this ball, right? You just kick this ball, and the mass of this ball is 1 kg, and velocity is 3 meters per second. So what is the energy it has? How much energy it has now? So that is kinetic energy is equals to half mv square. That's how we calculate. So half m is 1 kg, v is 3 square is, so like that. Half 1 multiply 3 multiply by 3 is 9, and so 9 multiplied by 1 by 2 is 4.5. So it has 4.5 joule of energy, kinetic energy. Everybody got that? See that? So you know the mass of the moving object, and you know the velocity of the object, and you can calculate the kinetic energy, right? So let's say you are driving a car, and then your car is moving, let's say 72 miles per hour, right? And then your car has, let's say, maybe 2000 kg. 2000 kg. Now you can calculate what is the kinetic energy of your car, right? So first of all, 7 miles per hour, you need to convert this into meter per second. So you can easily convert by doing Google here. So I'm even not using my calculator. So miles per hour to, let's say, Google here. So miles per hour. So miles per hour to meter per second. So meter per second, like this conversion. Miles per hour to meter per second. So is there a calculator? So let's say calculator. So miles per hour to meter per second, calculator. So like this. So now miles per hour, your car is moving with a 72 miles per hour. So that is 32.1. This is 32.1 meter per second. So this is meter per second. So so what is the kinetic energy your car has? Kinetic energy with your car now is half mv square. The mass of your car is 2000 kg. This mass is 2000 kg, and then velocities you have 32.1 2 times. You need to write 2 times 32.1 because we have formula 32.1 2 times. So you just calculate this one, and that many joule of energy your car has, the kinetic energy. Everyone got that? Yeah. So the velocity should be in meter per second, not in kilometer per hour or miles per hour here to find the answer in joule. Yeah. You got it? That's how we calculate the kinetic energy. So now potential energy. How to calculate the potential energy? So let's say from the ground, we need to measure the height from the ground. So let's say this is a ground. So it's a ground, yeah, ground. So I cannot go to the ground. So this is a ground. So this is ground. And let's say I have a ball here. So let's say the mass of this ball is 2 kg, right? 2 kg. And I measure the height of this ball from the ground. So let's say this is 3 meters, like that, yeah? Everybody got that? So the potential energy, how much potential energy this ball has? Potential energy is equals to mgh. So mgh. So m is 2 kg mass, and g is acceleration due to gravity, which is 9.8. If you take high school physics, you probably know that's 9.8 meter per second, and h is this 3 meter. So you multiply this one. So so it's approximately about 60, right? So about 60. 30, about approximately 60 joule energy it has now. You got it? You just put in the calculator and it gives about 58 something, yeah, which is close to 60. You got it? Potential energy is calculated like this way. So how about if it is just in 1 meter distance? So let's say the ball is right here. So just 1 meter distance here from the ground. So from the ground. So that would be potential energy is equals to mgh. So m is again 2 kg, z is 9.8, height is just 1 meter. 1 meter. So now it becomes approximately 20. You see that? 20 joule. So if the height is more, potential energy is more. Make sense? So the potential energy sitting here is low. The people, if you sit in the front bench here, your potential energy is low. If you sit all the way back in the height, your potential energy is high. Make sense? So basically, let's say a ball is falling from the sky to down in the ground, it can hurt more, right? Because it has too much potential energy, yeah. But if the body is falling from just from here to here, it cannot hurt more, right? It has a less energy. Make sense? Got it? Just like that. Good. So if the height is more, potential energy is more for the same object, yeah. Good. All right. So let's look. So we just finished that one. Kinetic energy, potential. So how about let's say we have a water here. Is it so in the molecular level, here is a kinetic energy. So you already know in the lab number 2, kinetic theory of gases, right? kinetic theory of gases. So the particle of this water are moving continuously and they have the kinetic energy. Make sense? So the particle, so look here, the thermal, the motion of the particle, thermal motion. So whatever the particle it has and this particle are moving continuously, that motion is called thermal energy. Mechanical energy, like the automobile is running, like the car is running. Electric movements, like you have the electricity coming in these wires in like the flow of the electron. Electron is just flowing. So these are the kinetic energy. Make sense? Electricity is a kinetic energy. So it is coming from the powerhouse to our house, right? So just these are the flow of the electron. Good. So they are called kinetic energy. And the potential energy is if it is not moving, they have kinetic energy. So let's look here. Chemical energy. So what is chemical energy? So chemical energy is like this one. So let's write the hydrocarbon. So this is a fuel. So this is a petrol basically. Hydrogen, hydrogen, hydrogen. So it's a methane, ethane, propane, butane. So these gases are called the fuel. So energy is stored in this bond, chemical bond. Make sense? So this is a CS4. It's a cooking gas or the petrol, right? This kind of the compound is a petrol. So the energy is stored in this bond. That energy is called the chemical energy. Make sense? In the food. For example, I drink some glucose or sugar. So glucose is C6H12O6. So like this. So C like this. So C, another C. So you have H, and like that. And somewhere there is a CHO. So there is an energy stored in this bond. And when I eat them, so our body just break this bond and release that energy for us, and we can do the work. Make sense? So that is called the chemical energy. Yeah. Everybody got that? So go home and then you take a Coke bottle. So 250 milliliter Coke bottle. They write here 140 calorie energy here. So there is a lot of sugar and they have this kind of bond, and all these bonds are broken from the sugar. It gives us 140 calorie energy. Make sense? So the energy stored in the chemical bond is called chemical energy. Make sense? So the energy in the food, the energy in the batteries, the energy in the, like when we burn the petrol and drive the car, all those energy are chemical energy. And when we burn them, either in the body or in the car, they release that energy and we can do the work. Everyone got that? So any energy stored in this kind of the chemical bond is called chemical energy. If we eat, our body breaks this bond and give energy to us. If we burn this in car, so these bones are broken and the car can run. Yeah. So because of this. Yeah. Good. Like that. So chemical energy, and chemical energy is also kind of the potential energy. Basically, this bone is not moving here, just sitting there, right? So the energy stored in the bone is a chemical energy. Now let's look this one. So we have been studying this law of conservation of something all the time. So what is law of conservation of? So law of conservation is we cannot make or destroy that thing. We can just change from one thing to another thing, right? So for example, let's say, so law of conservation of energy, law of conservation. So this is very important law. It's a very simple but very important law, law of conservation of energy. It's just like the law of conservation of mass. Mass cannot be created, mass cannot be destroyed. Therefore, we need to balance the reaction, right? Yeah. So I already told you why we should balance the chemical reaction, because mass cannot be destroyed or mass cannot be created, right? So the mass is mass of the reaction and mass of the product is always same. Therefore, we need to balance the chemical reaction. Exactly same here. So if you have some energy here, so you cannot destroy this energy. Yeah, you cannot make this energy. You can just change energy from one form to another form. Make sense? So for example, CS4. So CS4 is a chemical energy. So it is a chemical, so it has chemical energy. So maybe this chemical has, let's say, 40 joule energy here. Now I burn it, and it converts into the heat energy. So I get 40 joule heat energy. You see that? Heat energy. Did I destroy the energy? Did I make the energy? I didn't make energy. It was already there, right? It was already there. CS4, I didn't make CS4, right? It was already there. So it has the 40 joule energy. I didn't make it. It was here. right? I cannot make the energy, and I could not destroy this 40 joule energy. I just converted that 40 joule chemical energy to heat energy. Make sense? 40 was equal to 40. You got it? So we cannot make energy. We cannot. You see that how maybe at this time you might be thinking that we cannot make energy. How is it possible? We are all making this electricity, battery. We are making energy. You might be thinking that way. Don't think that way, because in the powerhouse also we are converting some kind of energy to electrical energy. So we get the coal and we burn the coal, right? Coal has chemical energy and we burn the coal, and the coal gives us heat energy. And with that heat, we boil the water and run the turbine, and turbine gives the electricity. So basically, we are converting that energy stored in coal to the electricity. Make sense? Are we making coal? We are not coal. We are not making coal, right? We cannot make coal. Yeah. So energy cannot be converted. Energy cannot be made. Energy cannot be destroyed. Energy can be converted from one form to another. So here we've converted the chemical energy 40 joule to heat energy 40 joule. I didn't make it. I didn't destroy it. I just changed it. Make sense? Everyone got that? Easy, right? Easy. So I give one example here. So let's talk about the hydroelectricity. So I come from Nepal, so we have a big mountains and big hills. So most of the electricity in Nepal is all about the hydroelectricity. We don't burn coal, so we don't have coal. So all energy comes from the water. So what we have here in the hill is, so we have hill here. So in this hill, we make big dam here. So it's a dam. So in this dam, we have water here, right? Water. So water is not moving here. So this guy has potential energy. Make sense? Potential energy. Got it? So did I make the potential energy? I didn't make the potential energy. Water is collected in that dam. So that dam has a potential energy. So what we do is we just put the pipe here, and then we open this valve here, and then water start to flow here with a very high speed, and this has a kinetic energy. Did I make the kinetic energy? I didn't make the kinetic energy, right? That potential energy is converted to the kinetic energy. You got it? Now we put a magnet and wire here. So I have a, let's say, horseshoe magnet here. So if you know the Faraday law of electromagnetic induction from your high school textbook, so this is a magnet here. We put magnet here, and there is a fan here. So something like the fan here, and then we put some wire here. So and wire here, and what happens is this flowing water start to hit this fan, and this magnet start to rotate. When this magnet start to rotate, the electricity is produced in this wire, and it comes to our house, right? See that? Did I make the electricity? We didn't make the electricity, right? So look here, there was a potential energy. We just converted to kinetic energy here just by letting it flow. And then that kinetic energy of the water just rotate this magnet, and this magnet rotates, and in the wire, the electricity is produced here, and electricity started to flow here. Now we have electrical energy here. Electrical energy. So now you bring the electrical energy to home, connect to the light, you got the light energy, connect to the heater, you get the heat energy, connect to the radio, you get the sound energy, right? So we don't make energy, we don't destroy energy. We just convert one form of energy to another form of energy. Everybody got that? So before I come here, I drink some glucose and I drink some protein. So I have a chemical energy, right? And I come here and I'm just talking and I'm producing the sound energy from that chemical energy. Have you got that? So I'm not destroying my energy. I'm just converting into those glucose or protein energy to the some sound energy. Got it? So energy cannot be created, energy cannot be destroyed, energy can be just converted from one form to another. And this is the fundamental principle of the thermodynamics. Yeah. So without this principle, no thermodynamics. Good. All right. So let's go down and look here. So in the molecular level, when you look in the molecular level, so we are just looking in the big things here. So let's look in the molecular level. So let's say I have some water here. So these are molecules here. So there are few molecules here. So if these are moving, so if these molecules are, if you look the second lab, in the gas, the molecules were moving very fast, right? In the liquid, they were moving slow. In the solid, they were just vibrating. So these molecules are moving in gas very fast, in liquid a little bit slower, and in solid very, very slow, but they are moving. So that kind of motion is called thermal energy. Make sense? Thermal energy. Got it? So let's say this is a 25 degree centigrade water. Thermal energy, this molecule are moving slowly. Yeah. So less thermal energy. Now I heat it and make it, let's say 80 degrees centigrade. Now this molecule start to move very crazily, very fast, right? Then kinetic energy becomes more. Thermal motion becomes more. If you got that? So if the temperature of the thing is higher, particles start to move faster and they have more thermal energy or kinetic energy. So a boiling water at 100 degrees centigrade, the molecules are really moving very, very fast and they have very high kinetic energy, yeah? Thermal motion. So as the temperature is more, particles move faster and they have more energy. Now, chemical energy, potential energy associated with the arrangement of particle is called the chemical energy. I already told you. So let's say this is C, like H, like H. So this is CH4. This is the fuel. So look here, the particles are arranged this way here, and then they have some kind of the energy. Now, if you bond it, the particles start to rearrange another way. So they will be arranging like this. Look here. So here is one kind of arrangement. Here is another kind of arrangement. Here is oxygen. Here is one kind of arrangement. Here is another kind of arrangement, right? So this kind of energy is called chemical energy. Basically, the energy stored in the chemical bond in chemicals is called the chemical energy. Make sense? Everybody got that? So if you read the book write very formal way, you know, formal way, very nice language, and a little bit harder to interpret. Yeah. So these notes are from books, but simply what is thermal energy? You don't have to talk about, oh, it's the energy due to the arrangement of the particle. You don't have to understand that way. You just say, okay, there is a chemical, and in that chemical there are bonds. The energy stored in these bonds are called the chemical energy. Everyone got that? So arrangement of the particle, meaning that particles are arranging a certain way here, a certain way here, different way here, different way here. So we can basically calculate the how much energy difference between these guys, and we will do in chapter 8 or chapter 9 later. Yeah, got it? So chemical energy is energy associated with the chemical bond in different chemicals. So this is very important. Extensive property and intensive property. So can I change your height? I cannot change your height now, right? So that's your your intensive property. Make sense? But I can change your chemistry knowledge now by teaching certain way. That's extensive property. Make sense? So extensive property depends on external thing. Intensive property is your inner property. Everybody got that? So just like that, extensive and intensive property. So let's look at extensive property. So extensive property means extensive property. So let's say you have this thing, and you have this thing, and you have this thing. So this guy has small quantity, big quantity, right? So this guy has small mass, this has bigger mass, this has bigger mass, right? So mass is an extensive property, because if you take small amount, mass is 1. If you take a bigger amount, mass becomes different. If you take a bigger quantity, the mass becomes even bigger, right? So mass is a extensive quantity, and you can just easily change just by changing the quantity, right? You got it? So look here, extensive property, a property that depends on the amount of material. So amount of material here is small, amount of material here is big, amount of material here is big. So if you measure the mass of this one is small mass, bigger mass, bigger mass. So mass is a extensive property. Yeah. Everyone got that? Extensive property. It just depends on the amount of the material. Now mass, and let's look the volume. So amount of the material. So let's say you take this much water, small volume. You take this much water, big volume. You take this much water, you have this much volume. You see that? So if you take a small amount, you have a small volume, right? Look here. So I have this much water, right? So it's about half liter. So if I put this much, it's about 0.75 liter. If I put up to here, it's a 1 liter, right? So how much I take, the property value changes. Make sense? Did you got that? So you'll understand later, yeah? Just we'll. So extensive property depend on the amount. Extensive property depend on amount of the material. So mass, volume, and energy. For example, if you take, let's say energy. So let's take 5 kg water, and let's say 1 kg water. So which water has more energy? Let's calculate. So potential energy we are calculating mgh. Look here. So this guy has 5, so that's 5 gh kinetic energy, potential energy. This guy has 1 kg water, potential energy is 1 gh. You see that 5 kg water has 5 gh kinetic potential energy. 1 kg water has 1 gh kinetic potential energy, right? So if you have a more water, you have a more potential energy. Make sense? Got it? So who has more energy? Ocean has more energy, or the lake has more energy? Definitely ocean has more energy, right? Because it has tons of water, right? Lake has small amount of water. Everybody got that? Or let's say one guy is a 60 kilogram, and these guys are fighting. So one guy is 60 kilogram, another guy is, let's say, 5 kilograms. So it's a baby is fighting with a 60 kg guy. Who will win? This guy will win, right? Because they have too much energy. Make sense? So like this guy has potential energy. M is 60. So M, so 60 GH. So 60 GH. You can put a height and this value. This is 60 GH. That guy is just 5 GH potential energy. So energy is also, it depends on the amount of the material, right? So how much amount this guy has? 60 kg, yeah, right? So mass, volume, energy are the depending on the amount of the substance, right? 5 kg guy has a small amount, a 60 kg guy has a big amount, right? Got it? Like that. Good. Now this is the extensive property. So mass, volume, and energy are extensive property. Now let's talk about the intensive property. Intensive property. When you know this one, and then you can easily differentiate. Intensive property. So take a big, go to the lake and put your thermometer right here. Thermometer right here. All right. So it was 21 degrees centigrade. So take a little bit water from here and put in the cup and measure the temperature. Still 21 degrees centigrade. You see that? Does the temperature depend on the mass? It didn't depend, right? So whether you take like thousands of tons of water here and measure the temperature, that was 21 degrees centigrade, and you have a small amount of water here and it's still 21 degrees centigrade. Now you got it, right? So temperature is an intensive property. So it does not depend on the amount of substance. How much substance you take, it doesn't matter. Make sense? So let's take another example here. So I take a let's say this is an oven, and I have another oven here. In one, I take a big amount of water here, and I put a thermometer. It starts to boil, and it reaches 100 degrees centigrade. And I put a very small amount of water here, and I put a thermometer, and it starts to boil again 100 degrees centigrade. Look here, temperature. Did temperature change depending on the mass of the material here? It did not, right? So you have a small amount of water here and put a thermometer, it is boiling. You measure the temperature of that boiling water, 100 degrees centigrade, right? Now you have tons of water here, it's boiling, put thermometer, it's still 100 degrees centigrade. So no matter you take small amount of water or big amount of water, the water boils at the same temperature. So temperature is independent of the amount of the water. Make sense? So it doesn't depend on the water. Temperature does not depend upon the quantity or the mass of the material. Yeah. So that's intensive property. Good. So let's look at the density. So this temperature is independent. To the amount of matter. Now let's look the density. Let's look a lot of water here. 1000 kg water here. 1000 kg water here. And let's take small like 500 gram water here. Now put a density meter here. So you already measured the density of water in the first lab. That was 0.99 gram per cubic centimeter, right? In the first lab. So put it. So we don't have to do the density that way. There is another way of doing the density measurement. There is a instrument called densitometer or some gravimeter or whatever they call, yeah, density. So let's say this one. So this is called density measuring. We used to use in another college. We used to do this way. Density measuring device. Density measuring device. Look here. They call density meter. This kind of thing. So they have. This is a hardness tester. So there are hydrometer. They call hydrometer here. So hydrometer. So this kind of the instrument they have. Hydrometer. 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 Okay, so they measure the density. So they have this kind of the instrument. Once you just put in the water or milk, they read the density themselves. We don't have to measure the mass and volume, and we don't have to divide mass by volume how we did in lab number 1. Yeah. So in the big laboratory, they just use this kind of the instrument to measure the density meter. You see, you just throw this guy into the water, and they show 1.4, 1.2, 1.3. I don't know how much is the density. So something like that. So throw your that density meter here, and it will show 1 gram per cubic centimeter. And put that guy, the same guy here, it will also show 1 gram per cubic centimeter. You see that 1000 kg here, 500 gram here, and you put the density meter in both shows the same reading. So density is a intensive property. It didn't depend on the how much quantity of water you took, right? Everyone got that? Good. Like that way. Good. So what else? So let's see. So density, for example, density is independent. Density don't depend on how much mass you take, right? Temperature don't depend how much mass you take. So there are many things which don't depend on mass. So let's take this heat versus temperature, and then we will stop here, and then we will. So what is the difference between heat and temperature? So temperature cannot do anything. Temperature is a useless thing. Temperature is just a useless thing. It cannot do anything. Make sense? So, but heat is very important. Heat is very important. It all does the work. Yeah. So temperature is just the effect. Heat is the real thing. Everyone got that? So to do work, we need heat. Temperature is just the indication how much heat would be there. So if it is a very hot, you think that, oh, there may be more heat, right? So temperature is the degree of hotness or coldness. Heat is the energy. So energy is important. That effect is not important. So temperature is not important thing. So you might say, oh, temperature is important because outside today is a 50, so I feel good. So that's just the effect of the sun. Yeah. So, but the sun is important. Make sense? So the effect, the degree of hotness or coldness of something is called temperature, and temperature is just the effect, and that's not important. Yeah. But the heat is the important. Heat is the energy that can make things hot, that can drive our car, that can make our house heat, right? So heat is important. So heat is the energy, and the temperature is just the effect of heat. So either degree of hotness, how much heat could be there. So by using temperature, we can estimate the heat. You see that? So heat it's very hard to. So how much heat in this room now? It's very hard to measure how much heat is now. But if I know the temperature, I have a couple of formulas. Just by using that formula, I can calculate the amount of heat in this room. Yeah. So in the next class, I will show you how to calculate the amount of heat in this room. Yeah. So it's very hard to measure the heat without knowing the temperature. But if you know the temperature, just put that temperature in one equation, and you know how much heat in this room is. Yeah. Everyone got that? So heat is important, which is the energy. It is the transfer of energy. It can do a lot of work. Everything is energy, right? So heat is just the energy, but the temperature is degree of hotness or coldness. So in the next class, we will continue from there. Alrighty, everyone. Thank you very much. Alrighty. Thank you very much.